So far we have seen how we can solve differential equations using numerical methods. Basically we have seen one numerical method, that is Euler method, and in Euler method the formula that we use to find different values of y along we move to the x-axis is y new is equals to y old plus slope into the step size. But there are other methods which are obviously better than Euler method and give us better approximation of the function y that we are trying to find out. So all of those methods fall into the category of improved Euler method. From that category, in this video we are interested in discussion of one method, that is Hume's method. Okay, let's see. Here we have put Euler method and Hume's method side by side. What is the upgradation from Euler method to the Hume's method? The upgradation here comes into the place of slope. In Euler method, we utilized the slope that is given in the form of differential equation. Okay. In Euler method, this is how the slope was calculated. If you are trying to find the value of y at new x, we would use the value of slope at the previous value of x. For Hume's method, there is a slight upgradation in the calculation of slope here. Here, we will use slope for two values. If we are calculating y at new value of x, we will calculate the value of slope at the new value of x and also calculate the value of slope at the old value of x, and then have an average of the two values and then plug that into the formula, and consequently we will find the value of new y. Okay, how it looks like, let us do the same example that we used for Euler method and let us see how it works out for Hume's method. Let's say we are given the same differential equation to solve. The task at our hand is to find the or draw the graph of y. From the initial value, we can plot this point on the graph. So we have one point on the graph already. So now we are interested in calculating the value of y at x equals to 0.5. So here everything will remain similar, but in the place of slope we will use value of slope at x equals to 0 and value of slope at x equals to 0.5, which here we get to see that value of slope at 0 is 1, value of slope at 0.5 is 0, and now we will take both these value and calculate the average of them and then plug them into the equation and find out the next value of y that is available at x equals to 0.5, which turns out 1.25. So now we have another value of y at x equals to 0.5. In the similar fashion, now we are interested in calculating the value of y at x equals to 1. So here we will need the value of slope at x equals to 0.5 and value of slope at x equals to 1, which we can see here both of the values have come out to be 0. So which means the value of y at x equals to 1 will remain unchanged. In the same fashion, now we are interested in calculating the value of y at x equals to 1.5. So we need the value of slope at x equals to 1 and also the value of slope at x equals to 1.5. And after the calculation we get the values as 0 and 1, and if we take the average of them and plug it into the equation, the value of y at x equals to 1.5 comes out 1.5. In this way, we can run our calculation for calculating the value of y at x equals to 2. This is how the equation pans out. So eventually, we get the value of y at x equals to 2 as 2.5. Okay. If we keep calculating the values of y at regular interval and put them into a table, this is how the values will look at the table, and if we plot them into the graph and see, this is how the graph looks like. The blue line is the exact function of y, and the points that are in the white we have calculated using Hume's method, and if we connect all the points that are in white, we can see we can almost get much closer to the exact function. How it is better than Euler method? Let's see here. Here at the right hand side is the solution that we got from the Euler's method, and at the left hand side is the solution we have got using Hume's method. You can obviously compare between them and come to a conclusion that obviously Hume's method gave us a better approximation of the function y than the Euler's method. So it is obvious that the improved Euler methods are better than Euler method, and one of the improved Euler method is Hume's method, which is quite evident in front of our eyes that it produces better result than Euler method. In continuation of this improved Euler method, next we will discuss Range-Kutner method.